Everybody, Dr. White back again for the final installment of our Calc 2 lessons, continuing with Taylor series, an interesting application to Euler's identity. So first, a review of imaginary numbers from high school. You remember the number I is your basic imaginary number, and it just like comes totally out of left field, and all it says about itself is that when you square me, I'm minus 1, okay? And so basically, I comes in to serve as the square root of minus 1, because there is no real number that you could square out to get minus 1. I serves as the square root of minus 1. And so like if you wanted the square root of minus 9, you could write it in terms of the I. You could say that's the square root of 9 times minus 1, which is the square root of 9 times the square root of minus 1. So that would be 3, the square root of 9, times I. And the square root of negative 13 would be the root of 13 times I. And this gets you what are called imaginary numbers. So imaginary numbers are a real number times the special number I. Okay. You may also be familiar with the concept of a complex number. A complex number is any number of the form a plus bi, where a is a real number and b is a real number. And the a is called the real part of the complex number, and the b is called the imaginary part because the bi is an imaginary number. Okay, so if you add a real and an imaginary, you get a complex number. So some examples of complex numbers. Actually, any real number counts as a complex number because you could write it as the real number plus 0 times I. So like 3 is a complex number. Negative 7 plus 2.5 times I is a complex number. 5i counts as a complex number because you can think of it as 0 plus 5i. Similarly, minus 3i is a complex number, 0 plus a negative 3i. And so even 0 counts as a complex number because it's 0 plus 0i. So you could actually, you can think in terms of there being two dimensions, like a real dimension and an imaginary dimension. And you could stick all your complex numbers on what we call the complex plane. Instead of an x-axis, what we've got is a real axis here, and it's just the real number line. Here's 0 right in the middle. And instead of a y-axis, we've got what we call the imaginary axis. And along it are the imaginary numbers. There's 0, which counts as imaginary because it's 0i. And here's 1i and 2i and so on and so on. And of course, all kinds of fractional times I in between. And then here's minus 1i and minus 2i and so on. And then we can stick complex numbers on the plane. Like if you want to stick 2 plus I on the plane, I'm going to stick it over the real number 2 and next to the imaginary number I. And I get 2 plus I. If you want 3 plus 2i, you go to 3 on the real axis, you go to 2i on the imaginary, and there's your 3 plus 2i. Okay. So another thing that you might have noticed about I when you were thinking about it back in high school is the powers of I. Like I to the 0, that should be 1 because anything to the 0 is 1. I to the 1 is I because anything to the 1 power is itself. I squared is minus 1 because that's what I does. It squares out to minus 1. But what about I cubed? Well, by rules of exponents, that should be I to the 2 times I to the 1. I squared times I. And I squared is negative 1, and negative 1 times I is minus I. What about I to the 4th? That would be I cubed times I. And we just found that I cubed is minus I, so we're looking at minus I times I. That's a minus I squared. Now I squared is minus 1, so we're looking at minus minus 1, so we get 1. I to the 4th is 1. What about I to the 5th? Well, that's I to the 4th times I, and we just found I to the 4th is 1, so this is 1 times I, which is I. How about I to the 6th? I to the 5th times I. And we just found I to the 5th is I, so we're looking at I times I, which is minus 1. And by the time we get down to here, we start thinking, wait a minute, I've seen these numbers before. We started off with a 1 and then an I, and a minus 1, and a minus I. And now we're at 1, and an I, and a minus 1. Hey, we're cycling around. And we're going to keep cycling around. Because every time you get an extra 4 powers, you've got another I to the 4th, which is a 1. You're just going to keep cycling around forever between 1, I, minus 1, and minus I, forever. So let's see what this can do for us. So mathematicians had been thinking about these kind of imaginary numbers for a little while in the 1700s. And the great mathematician Leonard Euler asked himself, well, okay, we got these imaginary numbers now. What if I tried to do ordinary math with imaginary numbers? Like, what if I tried to raise the number e to an imaginary number? So like e to the I times x, where x is a real number. So I times x is like an imaginary number. What would e to the I times x, what would it have to be if I followed all the rules of calculus that I've already proven so far? So he says, well, e to the ix, well, the Maclaurin series for it should be what you get by plugging ix into wherever you saw an x in the Maclaurin series for e to the x. So you get this. So writing that out, you have the 1 plus the ix plus the ix squared over 2 factorial plus the ix cubed over 3 factorial, and so on. And let's work with that a little bit. What if we squared out the ix? You'd have I squared x squared. And if you cubed out the ix here, you'd have I cubed x cubed, and similarly an I to the 4th x to the 4th, and an I to the 5th x to the 5th, and over their respective factorials. But Euler goes a little bit further, and he says, hey, I know about powers of I. Let me see what I can find out. In here, the I squared is a minus 1. So I've really got just a minus x squared over 2 factorial. In here, an I cubed is a minus I. So I've got a minus I x cubed over 3 factorial. The I to the 4th here is a 1. So that just leaves me next to the 4th over 4 factorial. The I to the 5th is back to an I. The I to the 6th is a minus 1 again. And, the next up would be an I to the 7th, x to the 7th over 7 factorial. But I to the 7th is going to be, well, continuing the cycle, of the 1 I minus 1. It'll be a minus I. So there would be like a minus. There would be like a minus I x to the, a minus I x to the 7th over 7 factorial there. And it would just keep on going. And he says, all right, I've got all these numbers added together. Why don't I just gather all the real numbers together and all of the imaginary numbers together? So like there's one here, and there's one here, and there's one here, and there'll be that minus I to the x to the 7th over 7 factorial there, and so on. Gather them all together, but also factor out their common factor of I. And when I stare at that a little bit, I realize, whoa, that is the Maclaurin series for cosine of x. And this is the Maclaurin series for sine of x. So all along, e to an imaginary number, ix, is actually cosine x plus I times sine x. That's what complex number it is. And that's called Euler's identity. So just some examples, trying it out for different values of little x. E to the I times 0 would be cosine 0 plus I sine of 0. That's a 1 plus I times 0. It's a 1. Which makes sense because e to the 0 ought to be a 1. How about e to the pi over 4 times I? I'm going to use some radian measures here because it's easy to find sines and cosines. E to the pi over 4 I. That's cosine pi over 4 plus I sine pi over 4 root 2 over 2 plus root 2 over 2 times I. Cosine e to the pi over 2i. Cosine pi over 2, I sine pi over 2, cosine of pi over 2 is 0, sine of pi over 2 is 1. I just get I. E to the pi I. works out to a -1. E to the 3 pi over 2i, cosine 3 pi over 2 is a 0, sine 3 pi over 2 is a -1, so I just get a -i. E to the 2 pi I is cosine 2 pi I sine 2 pi. Well, 2 pi is the same angle as 0, so it's going to be the same as cosine 0 plus I sine 0. It's still going to be, it's going to be back to the 1 that we were at right here. And so we have this kind of a same like going around feeling, But before we'll talk much more about that, I really want to just point out that this is absolutely one of my favorite identities. So it's saying that e to the 2 pi I is 1. And so I'm thinking, like, if you had to name some of the most important numbers in mathematics, what might you name? And you might say, well, 1's a really important number because it's the basis, of like all counting. And 2's a really important number because the square root of 2 was the first number that was proved to be irrational by the ancient Greeks. I mean, pi is clearly an important number, shows up everywhere. E is an important number, shows up everywhere. And I makes all this like square roots of negative numbers possible. And so here are 5 famous and important numbers in mathematics, and they're all related to each other by this identity. E to the 2 pi I is 1. So if somebody ever tells you that their sports team is number e to the 2 pi I, they're bragging. Their sports team is number 1. That's what they're saying. I want you to think back to the Cartesian plane, okay, with the unit circle. And if you have a theta radians there, you know that by definition, the coordinates of the point where you meet the unit circle are cosine of the angle, sine of the angle. That's in the regular xy plane. I would like you to now think about the complex plane with its real axis and its imaginary axis, I at the top minus I at the bottom. And I've drawn that same unit circle. So everything on the circle is 1 unit away from the origin of the complex plane, the number 0 here. And I've drawn an angle of x radians to this line segment up arching up to here. Because these coordinates were cosine and sine of the angle, this complex number here had better be cosine of x plus sine of x times I. That is e to the ix, according to Euler's identity. And so e to the ix actually just cycles around the unit circle as x changes. We found that e to the I times 0 was here at 1. We found that e to the 2 pi, the e to the pi over 2 times I was here at I. E to the pi I was a -1. Pi radians would point you back here, and there you are at -1. E to the 3 pi over 2. 3 pi over 2 radians is all the way to your pointing down here, and we found it was -I. E to the 2 pi I was 1, back around again. E to the ix just lands on the unit circle x radians away from the positive real axis. Wow. Amazing identity. And it was the basis for establishing a relationship between the real and the complex numbers through exponentiation. So that's all we've got for now and for the course. See you later.